Good day everyone, I'm VIPP Kapundal and I'm going to discuss the rivet connection. Before we proceed with the introduction, I'm going to discuss first what are the notations that we're going to use. So we have the pitch of the rivets, which is the symbol of small letter P, the diameter of the rivet hole. T is for the thickness of the plate, permissible tensile stress for the plate material, safe permissible shear stress for the rivet material, small letter N for the number of rivets, safe permissible crushing stress for the rivet or plate material, uppercase P for the steam pressure in boiler, capital letter D for the internal diameter of the shell, efficiency of the longitudinal joint, capital letter C for the constant, small letter M for the margin, small letter B for the width of the plate, PT for the maximum pull acting on the joint. This is the tearing resistance of the plate at the outer row, which has only one rivet. So small letter E for the eccentricity of the load, capital letter A for the cross-sectional area of each rivet, and x1, x2, x3, etc. for the distance of the rivets from OY, y1, y2, y3, etc. for the distance of rivet from OX, F1, F2, F3 for the secondary shear loads on the rivets 1, 2, 3, and etc. L1, L2, L3, etc. for the radial distance of the rivets. And then you have the angle, which is the angle between the primary or the direct shear load and the secondary shear load. So, introduction. A rivet is a short cylindrical bar with a head integral to it. So as you can see here in the picture, the cylindrical portion of the rivet is called the shank or the body, and the lower portion of the shank is known as the tail. The rivets are used to make permanent fastening between the plates such as in structural work, shipbuildings, bridges, tanks, and boiler shells. The rivet joints are widely used for joining light metals. So the fastenings may be classified into the following two groups, which is the permanent fastenings and the temporary or detachable fastenings. For the permanent fastenings, as you can see here in the picture, or in the name itself, permanent, these are the fastenings which cannot be disassembled without destroying the connecting component. Example of these are the soldered and the braced or welded, as you can see here in the pictures. For the second one, we have the temporary or the detachable fastenings. From the word itself, detachable, it can be disassembled without destroying the connecting component. Example of these are the screws. So let's proceed with the methods of riveting. The function of rivets in a joint is to make a connection that has strength and tightness. The strength is necessary to prevent failure of the joints, while the tightness is also necessary in order to contribute to strength and to prevent leakage in boiler, ship, and etc. When two plates are to be fastened together by a rivet, the holes in the plates are punched and trimmed or drilled. So punching is the cheapest method and is used for relatively thin plates and in structural work. And since punching injures the material around the hole, therefore drilling is used in most pressure vessel work. In structural and pressure vessel riveting, the diameter of the rivet hole is usually 1.5 mm larger than the nominal diameter of the rivet. So another method is the cold riveting and the hot riveting. When the plates are drilled together and then separated to remove any burrs or chips so as to have a tight flush joint between the plates, a cold rivet or red hot rivet is introduced into the plates and the point. When a cold rivet is used, the process is called the cold riveting. So as you can see here in the picture, this is the process and example. It doesn't need any heat and it is suitable for small diameter or non-ferrous rivets like aluminum and brass. For the hot riveting, as you can see here in the picture, it needs high temperature, or it needs to be heated in an elevated temperature, and it is suitable when riveting material is ferrous and or rivet diameter is above 10 or 12 millimeters above. So here's the example. Another method is the hand riveting and the machine riveting. So the hand riveting causes the shank to expand, thus filling the hole, and the tail is converted into a point. As the rivet cools, it tends to contract, while the machine riveting is the die part of the hammer, which is operated by air, hydraulic, or steam pressure. So these are the examples and their differences. Let's move on with the important terms used in riveted joints. So first is the pitch. As I said earlier, the symbol is small letter P. This is the distance from the center of one rivet to the center of the next rivet measured parallel to the seam. The next one is the back pitch. This is the perpendicular distance between the center lines of the successive rows. The third one is the diagonal pitch, which is the distance between the centers of the rivets in adjacent rows of zigzag riveted joint. And the last one is the marginal pitch, which is the distance between the center of the rivet hole to the nearest edge of the plate. Let's move on to the failures of riveted joint. The riveted joint may fail in the following ways. Number one is the tearing of the plate at an edge. A joint may fail due to tearing of the plate at the edge. So this can be avoided by keeping the margin using this equation, which is the m equal to 1.5 diameter. So here is the example. As you can see here in the picture, we will apply that later on our example. The second one is the tearing of the plate across a row of rivets. We know that tearing area per pitch length is equal to the P minus D multiplied by the thickness. P stands for the pitch, D for the distance, and T for the thickness. And the tearing resistance or pull required to tear off the plate per pitch length is computed by using the formula tearing area multiplied by the tensile stress, or as you can see here in the picture, this one, sinubstitute lang siya dito, kaya nag-come up tayo ng P minus D multiplied by T multiplied by the tensile stress. So, yan. As you can see here in the picture, yung tear niya is across the rivets. The third one is the shearing of the rivets. Shearing of the rivets can be computed in single shear. It is computed by the pi over 4 t squared, and in double shear it is computed 2 multiplied by the area, pi over 4 t squared. So for the shearing resistance or pull required to shear off the plate per pitch, it is computed using this formula, which is the letter N multiplied by the pi over 4 t squared, and the last one is the 2 multiplied by the N, which is the number of rivets, pi over 4 t squared t. So as you can see in the picture, these are the examples of the shearing of the rivets. So the next reporter will discuss what are the types of joints that we're going to use. So this one is the shearing stress, letter A for the lock joint, letter B for the butt joint, and the last one is the double cover butt joint. Take note that this type of failure will occur when the shearing resistance is greater than the applied load per pitch length. The last one is the crushing of the plate or rivets. We know that crushing area per rivet is computed using the area of the crushing area, which is distance multiplied by the thickness, and the total crushing area is computed using the number of rivet multiplied by the distance and the thickness. The crushing resistance or pull required the rivet per pitch is computed using the number of rivets multiplied by the distance, the thickness, and the crushing stress. So take note that this type of failure will occur when the crushing resistance is greater than the applied load per pitch length, and the number of rivets under shear shall be equal to the number of rivets under crushing. Let's move on to the example para mas maintindihan natin. A double riveted lump joint is made between 15 mm thickness plates. The rivet diameter and pitch are 25 mm and 75 mm respectively. If the ultimate stresses are 400 megapascal in tension, 320 megapascal in shear, and 640 megapascal in crushing, find the minimum force per pitch which will rupture the joint. If the above joint is subjected to a load such that the factor of safety is 4, find out the actual stresses developed in the plates and the rivets. So we have here the given, the thickness is equal to 15 millimeter, the distance is 25 millimeter, the pitch 75 millimeter, ultimate tensile stress 400 megapascal, shearing stress which is 320 megapascal, the ultimate crushing stress which is equal to 640 megapascal. So for the first, let's find first the minimum force per pitch which will rupture the joint. Let's find for this first the ultimate tearing stress, tearing resistance of the plate per pitch. So it is computed using the formula as I said a while ago, the pitch minus the distance multiplied by the thickness and multiplied by the ultimate tensile stress. So let's input the values, 75 minus 25 multiplied by 15 and multiplied by 400, and the answer is 300 Newton. For the ultimate shearing stress of the rivets per pitch, it is computed using the formula of number of rivets multiplied by pi over 4 multiplied by d squared and multiplied by the ultimate shearing stress. So the number of rivets is 2 because there are 2 rivets only. Let's input now the values. 2 multiplied by pi over 4, 25 squared multiplied by 320, and the answer is 114,200 Newton. So for the ultimate crushing resistance of the rivet per pitch, it is computed using this formula, number of rivets multiplied by the distance, thickness, and the ultimate crushing stress. So let's input the values, and the answer is 480,000 Newton. So if we're going to compare the results, the minimum force per pitch will rupture from the joint 300 Newton. So the answer is 300 Newton. So the actual stress produced in the plates and the rivets. Before we proceed with the actual stresses, let's identify first the safe load per pitch length of the joint. So as said in the problem, it has a factors of safety which is equivalent to 4, and to know the safe load, let's divide the minimum force that will rupture the joint all over the factor of safety which is equivalent to 4, and it is equivalent to 75,000 Newton. So let's proceed with the computing of actual stresses. So let's move on to the actual tilting resistance of the plate. It is computed with the same formula a while ago, but the difference is we have our safe load. And now we are looking for the actual tearing resistance. So 75 equals pitch minus distance multiplied by the thickness multiplied by the actual tensile stress. So let's substitute the given, and we have 750 actual tearing stress divided safe load over the actual tearing stress. So the answer is 100 megapascal for the actual tearing resistance. The second one is for the actual shearing resistance of the rivets. So using the same formula again, let's substitute what are the givens. So 2 multiplied by the pi over 4, 25 squared, actual shearing stress, and 982 actual shearing stress, and the safe load divided by the 982, and we come up with this 76.4 megapascal or 76.4 Newton per millimeter square. And for the last one is for the actual crushing resistance of the rivets, we have here the same formula but different load. So we have 2 multiplied by 25 multiplied by 15 multiplied by the unknown, and 75,000 over 750, and we come up with 100 megapascal. So that's all. Thank you for listening.